Hi, in this video I'm going to teach you how to perform hypothesis testing using the separate variance t-test for two population means when variances are unknown but assumed to be equal. In addition to this condition, we need to consider that the samples must be independent. So samples are independent and the sample sizes are small. So that means N1, the sample size 1, is less than 30 and sample size 2 is also less than 30. Once you recognize the problem as a separate variance t-test, the test statistic that you will be using is t equals x1 bar minus x2 bar minus mu d, so similar to the other t-test, square root of s1 squared, that's the sample variance 1, over n1 plus sample variance 2 and 2. So pretty similar with the z formula. Now since this is t, we need to compute for the degrees of freedom. So the degree of freedom is calculated by, so let's name it df. We have a fraction S1, sample standard deviation 1 over N1 plus, so that should be variance, and then variance 2 over N2, and then you square, and this is over, so another set of fractions. We have variance again over N1, which will be squared, N1 minus 1. This will be added to variance 2 squared over N2, which will be squared over N2 minus 1. So do not be overwhelmed with the formula for the degree of freedom, because all you need to do is to place the corresponding numbers on the formula. S1 squared is sample standard deviation squared, sample size 1, sample standard deviation 2, which you will square over sample size 2, and once you put those numbers, you square and then over. Then you repeat the process by putting the corresponding numbers in the formula. So it will take you some time to compute for the value, but it should not be that difficult to place in the numbers. Also, you do not do this manually, so you can input the numbers in the calculator directly. So make sure you use a natural display calculator when you perform, or when you compute for the degrees of freedom, or even when you compute for the t value. Okay, so the key here is, first you need to identify whether the problem will fall under the separate variance t-test for two population means. To fully understand how to perform the hypothesis testing in this type of given information, let's look at one example. Suppose a study is conducted to determine whether a computer-assisted individual-based training will have a different effect to that of a traditional lecture and demonstration approach in training new employees. Let us say that in a certain company, there are 40 newly hired employees. They were divided into two groups of 7, with the first group receiving the computer-assisted program, while the other group under the traditional approach. On one part of the training, they learn how to set up a particular equipment. After the training, each employee was evaluated on the time it took him or her to set up the equipment. The data from the study are tabulated below. As we can see, the numbers, these times, are in minutes. So we have 10.2, 11.4, 8.5, up to 12.9 for the computer-assisted program. And we also see the time for the traditional approach with 7.5, 10.9, and so on to 9.6. For this problem, we want to check is there sufficient evidence to conclude that the employees under the computer-assisted program are faster than those who are under the traditional approach in setting up the equipment. And in particular, we want to assume that the variances of the assembly time of the two programs are unequal. The level of significance to be used in this test is 5%. We will start with our testing by setting up the parameters for the two populations. So first step is let mu1 be the true average time of people or the employees under the computer assisted program in terms of setting up the equipment, and mu2 be the true average time or setup time of people under the traditional approach. So once we set the symbols for our parameters, we can now state our null hypothesis and the alternative hypothesis. Take note that the claim, or what we want to test here, is whether those under the computer-assisted program are faster in terms of setting up the equipment. So that means if they're faster, their average time should be smaller than the average time of those who are under the traditional approach. So we could start actually by setting up our H1, that is, we want to test whether mu1 is less than mu2. And by default, we have to say that the mu1 is just the same as mu2, meaning there is no difference in terms of the average time, or at least there is no significant difference. Of course, the numbers will not be entirely the same, but is the difference really significant? That's the question. Okay, because they might differ in terms of very small value. So this is our HO and H1, null and alternative hypothesis. Then after that, we go to step number 2, that is to identify our level of significance, which is already stated as 5%. So 5% is 0.05. In number 2, this is also where we have to indicate any information about or any given information or something that we need to compute prior to the test statistic value. And we will know what to compute here because our formula will require the following. We need the x bar 1 and x bar 2. Well, the mu d is the mean difference. If they are assumed to be the same, then their difference must be 0. Then we need the variance of the first group and variance of the second group. We need n1, the sample size 1, and then the sample size 2. So to organize this needed information in your solution, what you can do is just list them down one at a time. So we need to find x1 bar, and then we need x2 bar. We need s1 squared, or you can find the sample standard deviation and then you square. You need to know what's n1. You have to know s2 squared and then n2. Again, noting that mu d is equal to 0 because as for our null hypothesis, mu1 is equal to mu2. If they're the same, then mu d is equal to 0. Okay, so what we have is the data. So the sample means are not yet given, the standard deviation or the variances are not yet given. So we have to compute for these values. Okay, so prepare your calculator for the computation. I'll do my computation and then I'll just write the values once I completed the computation. To calculate the values, I use Casio FX991EX, the class Swiss version, because this will just allow me to input the numbers using the statistics function of the calculator, and once I input all the values, I could easily calculate all the needed, or I can easily show or see the values, and the calculator will do the work for me. For the computer-assisted program group, I was able to calculate the sample mean to be 11.2143. I'm using 4 decimal places so that I can have 2 decimal places in the final answer, and this will allow me to lessen the error or the changes in terms of the final value, because if I will start with 2 decimal places and also writing the final answer in 2 decimal places, there might be a big difference to the actual value that we need to obtain. So for me, I suggest when you do calculations in the middle or in the middle of the solution, make your values rounded off to 4 decimal places. So I have the S1 squared. This is the variance. Okay, so this is already the square of the sample standard deviation, and what I obtain is 3.3248. Well, the sample size 1 is equal to 7 because we have 7 values for the data. My approach in calculating these values is that I first work on the first group, then calculate all the needed values. So once I'm done with the first group, I erase all the data in my table and input the data of the second group, which is the group under the traditional approach. For the group under the traditional approach, the sample mean that I was able to obtain is equal to 11.3714. The variance for this second group is 7.3 or 6390. So if you compare the variance of the two groups, we have a higher variance in the traditional approach. So that means the data in the second group is more, there's a more variance, so they are spread out with respect to the mean. And then the sample size 2 is still 7 because we have also 7 values for the time in the second group. So once we are done with the summary of the values that we need, we can go now to step number 3. And step number 3 is the calculation of the test statistic. So the test statistic value is statistic value. And because we have 2 population means, the variances are unknown but they're assumed to be unequal, we'll be using a t-test, and the t-test statistic formula is t equals, so the one that we used earlier, x1 bar minus x2 bar minus mu d, and this is all over the square root of the variance squared of the first group, the variance, the sample standard deviation squared, over n1 plus variance 2 over the n2. And then we place the corresponding numbers in the formula. So we have x1 is 11.2143 minus 11.3714 minus the mean difference, which is 0 because in the null hypothesis they are the same, or assumed to be the same. And then S1 squared is 3.3248. Note, this is already the variance and not the standard deviation. Over N1, 7, plus we have 7.6390 divided by 7 as well. Then let the calculator work for you and calculate the value. So I got negative 0.1255. Okay, then after finding the test statistic value, we compute for the degrees of freedom, or the DF. The degrees of freedom formula is, so let's refer to our formula, degrees of freedom. So this is the one that we need. So S1 squared, let's get this. Degree of freedom formula. Then let's input the numbers. So we have the following, and then when we compute for the exact number, and this is equal to 10.3911. Okay, so for the degree of freedom, if we have a decimal value, the rule is you have to drop the decimal value and round it down. So the degree of freedom must be 10. Okay, so do not make it 11. So even if the number is higher than 0.5, say you have 0.7933, you do not round this off to 11, but you have to drop the decimal value and then just maintain the whole number 10. Okay, so we will now get the draw the diagram. That's for step number 4. So diagram is, okay, this should be one-tailed. This is based on our H1. Mu1 is less than mu2, so the direction of our diagram should be to the left. So that's my key. So I will know that I have to shade the diagram, or the tail, on the left. So this is where, or this is our alpha. This set of numbers here is our critical region. Now to know the critical value, so the boundary is the critical value, we need to consider our alpha. So T of alpha is T of 0.05 with degrees of freedom that we have calculated as 10 in step number 3. So we have to refer to our T table. So use the T table to locate the T of 0.05. That's on your first row, and then down to the 10th degree of freedom. So whatever the number indicated there, that is the value that we have to use. So according to my list, so I have to refer to the T of 0.05. This is our T of 0.05, and the degrees of freedom 10 is here. So the number that we need is 1.8125. So 1.8125. So since it is on the left, we have to make use of its negative value, negative 1.8125. So once our critical value is plotted or identified, we go back to our T computed, the T statistic value, and it says negative 0.1255. Locate that with respect to our critical value, and we should be able to identify or locate that somewhere here, because this is at the 0 mark and we have negative point, that's about 1255, 0.1255. So it should be before the negative 1.8125 if the direction is going to the left. Now since the number is somewhere here, it went outside our area of rejection. So that means, so with that, we now create our conclusion. Number 5, again, since it went outside the area of rejection, then we say that we failed to reject HO. So that means there is no sufficient evidence supporting our H1. That is, we were trying to support the claim that mu1 is less than mu2, and that is the one with the computer assisted program, the group under the computer assisted program should be able to set up the equipment faster. Okay, but there's no sufficient evidence, so we have to keep our HO, which is mu1 is equal to mu2. That means they just perform at the same average time. So regardless of whether an employee will undergo a computer assisted program or under the traditional approach, there is no significant difference. Both of the groups will perform or will be able to set up the equipment on the same average time. Okay, so as you can see, the process of hypothesis testing is the same for all. They just differ in terms of what formulas you are going to use. If you are going to use the Z or a T, are you going to use a formula based on the variances? So you have to check whether they have this. We have to assume that the variances are equal or unequal. So having a set of formulas will be very important, because you have to select the formulas based on the information and the instructions that were given to you. Like in our problem, the instruction was to assume that the two variances are unequal, okay, given the two population means. Okay, so that's how you do hypothesis testing when it comes to two populations when the variances are assumed to be unequal. Okay, so that's it.